All right, so this is our pH scale and pH calculations notes on pages 7 and 8. And we're going to talk a little bit more about the pH scale itself instead of just the calculations and how to do them, just for some of the context of what we're doing and where all of these crazy calculations came from. So pH has actually been around for a while. Friedrich Kohlrausch around 1900 found that no matter how pure water was, it still conducted a very small amount of electric current, which means that H2O on its own must somehow have ions in order to conduct electricity, proving that water must self-ionize, react with itself to form some ions. And you see that reaction below. And that means that water is what we call amphoteric. We talked about this word a little bit at the beginning of our unit, those basics. Just means that it can act like an acid or a base. So it can react, dissociate with itself to a slight extent. Only about 2 in a billion water molecules are going to be ionized at any given moment. But if we've got ions, we can conduct electricity. Now, Friedrich Kohlrausch did a lot of experiments finding out these numbers and amounts, and he figured out that in pure water, the concentration of OH minus hydroxide ions is equal to the amount of H plus ions, which is still why we call it neutral. Doesn't that mean that it has no ions in it, no H's or OH's, just that they're the equal amounts. And in pure water at 25 degrees Celsius, those concentrations were equal to 1 times 10 to the negative 7th, which isn't zero, but it's so close to zero for most people's purposes. Water is pure H2O. It doesn't ionize enough to pay attention to. But of course, chemists, we do. And so this autoionization is a reaction, which means we can write an equilibrium expression for it, the K value, K expression for it, and you see that down below, Kw equals H3O plus, which is the way that the H plus actually exists in nature, in real life. H plus is too tiny and unstable on its own. And so if H plus is produced in solution, which is what that aqueous, AQ means, in water, around water, the H plus is going to grab onto that water to become what we call the hydronium ion, this H3O plus thing here. So you're going to see that a lot of times in place of just H plus. I do still have a lot of H pluses in your notes, and I'll talk about kind of why I do that when we get a little more into those calculations, but you on the AP equation, so you will see it as H3O plus everywhere. So if we know those concentrations of that H plus and OH minus ion to be 1 times 10 to the negative 7th, then our K value, the Kw, meaning the K value for the water ionization, is equal to 1.00 times 10 to the negative 14th. And I know I have that 0.008 there. The AP equation sheet just has the 1.0 and the times 10 to the negative 14th. So if you wanted to, you could kind of sort of scratch out the 0.8. If we take more precise measurements, including of these concentrations over here, then we can get some more sig figs in our answer over here, but doesn't really make sense right now without them. But there are some more digits down there if we take more precise measurements, which we can nowadays because it's not the 1900s. Anyhow, so we've got this expression for our equilibrium state of water. And remember, we don't include liquids, which is why we don't have any water H2Os in that K expression. It is constant. And, fun fact, apparently a 55.6 molar is the value that we use for the concentration of water in water. So it's a constant value. The other thing that while we're here talking about this Kw that will become more important later, but I will remind you of, is that Kw value, the K of water's reaction, is equal to the Ka, kind of the equilibrium power or meaning of that substance, times the Kb. So the ability or equilibrium state of our substance to be an acid times the ability for it to be a base is equal to our Kw. And we'll get more into that when we talk about weak acids and bases. But that for water, its ability to act like an acid and base are equal, It's that 1 times 10 to the negative 7th number. For other substances, they are different, but this actually lets us convert between them. But we'll get to that later. So, knowing about those OH and H plus concentrations lets us talk about how acidic or basic a solution is. And like I talked about with water, just because something is acidic doesn't mean it has no OHs in its solution. It just means that it has more H pluses than OHs. So, pretty quick basic reminder here on this page with these 3 bullet points. If the concentrations are equal, then it's neutral. If we have more OHs, which is the ion we generally think of with bases, we have more OHs than Hs, then it is basic. If we have more Hs than OHs, then it is acidic. And keep in mind, we've already learned about equilibrium and the fact that our K values are going to change, and we're actually going to see that in a little bit more detail. Get reminded of that in the lower half of this page when we do some calculations. But K values are temperature dependent, which means that an acid's and base's strength and their pH of a specific solution that's already been made can be affected by temperature, because that's going to affect the ionization of it. So the exception in general is anything we already know and consider strong is going to stay strong because their K values are so large that the temperature doesn't tend to cause any overall changes, or it changes something from having like a K of 1000 to having a K of 1001. It's like that's not a significant enough difference to matter. It's still so strong it completely ionizes. So let's do some quick calculations with this K expression, this KW expression, and before we get into the pH scale and pH calculation specifically. So if we wanted to calculate the concentrations of these 2 key ions in a neutral solution of water at 60 degrees Celsius, we have this K value at 60 degrees Celsius, which is different than the K value we showed you up above, which was at 25 degrees Celsius, and that'll become important later. But if it says that it's neutral, then that means that our H plus concentration is equal to our OH minus concentration. And if we use that K value, which remember, that K of water is going to be our H concentration times our OH concentration, products over reactants, but our reactants are liquids, so they don't exist. If those are equal, then we can kind of simplify this down to whatever their concentration is, it's X. And since they're equal to each other, then it's going to be Kw equals X squared. And just like with our solubility equilibrium, realizing it's an X squared situation tells us that all we've really got to do is take the square root of that K value, that 1 e negative 13. If that's equal to X squared, then we square root each side, and that tells us that X is equal to 3.162 e negative 7. That's our unrounded answer. I did only give you 1 sig fig here, so I am going to round this to just 1 sig fig. 3 times 10 to the negative 7. That is our molarity. I might as well write of both of those ions it was asking for. They are equal to each other and specifically equal to this number, at least at this temperature. So slightly different concentration than at 25 degrees Celsius, but it is still neutral. They are still equal to each other. So now using this idea and just bringing back a little bit of equilibrium, keeping those skills sharp, and Le Chatelier's principle, predict whether the reaction above, this autoionization of water we've been talking about, is exothermic or endothermic. And we have to do this by comparing the K value that we've got here at 60 degrees Celsius to the K value that we have on our equation sheet, 1 times 10 to the negative 14th at 25 degrees Celsius. And the question we need to make sure that we're answering is if it's endothermic or exothermic. And you might not know that immediately. You might need to think through some things, but it's always a good idea to write down your answer very clearly. You know I'm a fan of the CER structure for explanations and answers. Make your claim, solid evidence, and then support it with reasoning, which is what I'm going to use here. But if I'm not quite sure what my answer is yet, I can always leave a space. The reaction is either endo or exothermic. So I've got the endo is something othermic. I'm going to come back and make sure to fill that in before we leave, but I'm going to put that there to make sure I answer my question. And then I need to look at the facts, the evidence. Well, when temperature increased from 25 to 60 degrees, the K value did what? It's hard facts no one can argue with. Well, it went from 1e negative 14 to 1e negative 13. That means it got bigger. So the K value also increased, which means that temperature change that we saw happen, the 25 to 60, caused a reaction to shift towards which side? Reactants or products. Well, my K value is getting bigger because my exponent's getting smaller. So if it's getting bigger, that means that we shifted towards the product side. So our reaction shifted towards the products when that temperature increased, which shifting towards the products only happens if the thing we're adding, heat in this situation, is a reactant. And because heat, it has to be a reactant to shift us towards the product side when we add more of it. Then if heat's a reactant, it's going into our reaction. This is endothermic. Fill that back in at the beginning after I finish reasoning through this connection between our heat change and our K value change. So never be afraid to kind of work this through on paper and write down your thoughts as you're doing it and come back around and fill in that answer at the end. But if you're going to leave the answer to the end, at least make sure you solidly answer the question before you move on. It's always a shame to miss the point if you don't explicitly state it. So at this point, we've talked about the basics of the kind of origin of the pH scale. And really the pH scale itself came about because these concentrations we're dealing with are so incredibly small in this scientific notation. Even kind of the heaviest or most concentrated solutions are approaching 1 in their concentrations. So it's pretty rare to have anything in kind of normal number range to talk about. So scientists decided to start taking logs, which change those crazy exponent scientific notation numbers into more normal seeming numbers. And that's really all that we need to know and worry about there, is that logs turn this into normal numbers. A scale generally regarded to go from 0 to 14, although we have discovered and created work with some acids and bases that go off scale, that are above 14 or below 0. It is possible to have negative pHs, but not most of the time. It's extreme cases. So we have this scale, and literally the pH scale, P just means negative log. We're going to see a lot of that. We're going to see some pKa's and pKb's. It's just the negative log of the Ka value, the negative log of the Kb value. There's a pOH thing. That's the negative log of the OH concentration. Knowing that simplifies a lot of this from memorizing and finding equations. Just, oh, it's the P this, the P that. It means negative log this or negative log that. So pH scale just means we took the log of things. Negative made them positive numbers generally instead of negative. So it's just to make a nice, neat scale with normal-ish numbers to talk about how acidic or basic something is. So I have a lot of equations for you here that kind of reinforce each other, that are important for pH calculations, and all of these equations are on your AP equation sheet in some form. Remember, we've got things like our K expression here that has the H3O plus instead of the H plus. And I mentioned that I tend to use the just plain old H here because I think that reinforces this idea of pH being the negative log of the H concentration. Any of the H stuff goes together. Sometimes it's harder to make that link and that connection when it's H3O plus all over the place. They are the same thing, but in terms of getting started and getting familiar with things, I'm going to use just the plain old H in our kind of pH map, and concentrations generally the way that I write them, even though they are equivalent. Unless the question specifically asks for H3O+, I don't generally write it, but they are equivalent. And that's what you see on your AP equation sheet. So we also have the basic pH equation there, also with H3O+ in it. The pOH equation, which remember, P just means negative log. This is the negative log of the OH stuff, if it's pOH. And then we do get that reminder that the pH plus pOH equals 14. And that 14 number is just the pKw. So it's really just the negative log of this Kw expression. You can have the pH, the pOH, multiplying logs turns into adding their products, and pKw is just the negative log of the Kw, which happens to be 14. So these are all very kind of circular, self-reinforcing equations here. And you've got all of the main ones that you need. You do need a couple more, which is why I have added an extra map here in addition to this kind of slightly different visual scale of the pH scale here with these basic equations. And we're going to do calculations with them in just a second, but I do want to start by looking at this pH map, this kind of circle, square looking thing over on the side of the page. And I've highlighted the two equations that you kind of need to navigate between these four different types of values. These are the four different things you could be asked to calculate regarding pH, pOH. Is their concentrations or their pH and pOH. And like I said before, they're all pretty circular, reinforce each other, and kind of align with each other. But the one, really technically two, but they're both kind of the same. What do I do in order to find the H plus concentration or the OH minus concentration if we already have the pH or the pOH? Basically the reverse of that negative log step that is on our equation sheet. And if you're familiar with logs and algebra with logs, this log is really log base 10, and in order to undo a log, you take the base number, which in this case is 10, raised to the power of the answer we were getting out, which is the pH. And technically we move this negative over onto the pH side. So we're doing 10 to the negative pH to undo the log of the H plus concentration, to solve for that H plus. That's not algebra you're going to have to do. If you just remember that it's 10 to the negative of whatever you've already got. If you got the pH, it's 10 to the negative of the pH. And because that's the H stuff you're working with, it's the OH concentration you're going to be getting out of that. If you do 10 to the negative of the pOH, then you're putting OH stuff in. If I can get that there. Then if we're taking the negative log of the 10 to the negative of the pOH, we're going to get the OH concentration out of it. Just keep it in mind. H's go with H's, OH's with OH's. P means negative log. So if you're looking for the pOH, you're taking the negative log of the OH stuff. If you want to undo that, if you've got the pOH and you need just the normal OH, you have to undo that log. You've got to do 10 to the negative power of that pOH. So it gets a little bit messy. I know these scribbles definitely look kind of messy, but that's basically means that what we're seeing up on top with the H stuff is the same equations down bottom. Then we've got to be able to kind of navigate between our H side of things and the OH side of things, which means we can use that idea that the pH and the pOH add up to 14, or that the concentrations, if we've got both of those, or one of those, we can find the other by doing our K value divided by whichever one we know will get us the one we don't know. A lot of people mess up scientific notation in their calculator, honestly, especially when dividing by scientific notation numbers. So in honors, I always recommended you not go this way unless you are confident with your calculator skills, because you can always, even if I'm trying to get from here to there, you can always do some simple, reliable steps to get there. It's just a couple extra steps, a couple extra button pushes. So you can always use it. It is there and it's on your AP equation sheet, but if you put it in the calculator wrong, then you're going to get the wrong answer out, and that'd be a shame. So this is really half about knowing and finding the equations you got to use, using them. The other half is just calculator skills. Can I put it in my calculator correctly in order to get the correct answer out? So I would encourage you, as we start working some of these problems, yes, I'm going to work all of the problems on this page, but find your calculator, the one you're going to be using hopefully, or an emulator online of the calculator if you don't have your own handy. But just try and follow along. See if you can push the buttons on your own calculator, or in Desmos, I suppose, since that's always an option on the AP exam, and see if you can get these same answers, because if you can't, then I need to help you with some calculator skills. No matter how good your math is on paper, if you can't put it in the calculator right, we're not going to get those points. So let's look at these problems here. We are given a single concentration, and the concentration we're given kind of varies in each problem. Here I'm giving the molarity of my OH solution, and here I'm being given the concentration of an H plus based solution. And so the process we're going to go through is going to change in each problem, but we are going to calculate both our pH and our pOH, and then whichever of the two concentrations that we are missing. If we've got the H, then we're going to look for the OH. If we've got the OH, we're going to look for the H, just to fill out all four of those kind of key quantities that we can calculate for pH from that map. And then we're also going to make sure to come back around before we move on at least and classify our solutions as neutral, acidic, or basic. And keep in mind, we should always be using the pH value to do that. Technically, you can use the pOH value, which you might find quicker in some situations, but it's always one step away, and it's a lot more reliable to just count on one value, because all the numbers are opposite for the pOH scale, so you got to be careful with that. But here, if I am given an OH concentration in this part A, anytime I'm given a concentration, my instinct is to take the negative log of that value. So if I'm taking the negative log of an OH concentration, that means I am calculating and finding my pOH here. So I can type in my negative log of 1.0 times 10 to the negative 5, and your calculator will tell you that the answer to that, our pOH, is 5. Now, quick note about sig figs here. The base of our scientific notation is the sig figs for that number, and after we take a log of a number, we need to keep the same number of sig figs in our answer. So even though the calculator just told us the answer is 5, our pOH to 2 sig figs would be 5.0. Now, once I have my pOH, my immediate instinct is to calculate the pH from that, because they will always add up to 14. So I can do 14 minus 5. And here we've got to remember, since we're doing subtraction, we don't actually care about sig figs. What we care about and what we round based off of is the least number of decimal places in our values. And we don't round based off of constants like 14, because technically that is an exact number. It's exactly 14, and so that could be written as 14.00000 with infinite sig figs. So we're not going to round based on the 14. We're going to round based off of our number and its decimal places, which is 1, which means we're going to keep 1 decimal place in our answer, meaning our pH is 9. Now that I've got my pH, I can find my H plus concentration one of two ways. I can either take this pH and calculate the H plus concentration from it directly, do 10 to the negative of that pH, or I can do that Kw value divided by my original given value that I had all the way back here. Since that's my OH concentration, I can either go either way. And I think since I already have this pH, it's less button pushes and a little bit more reliable to do 10 to the negative of that pH value. So I'm putting in my calculator 10, a solid color, 10 to the negative 9.0, and it tells me my answer is 1 times 10 to the negative 9. Basically just got rid of that decimal point on the 9 and added this 1.0 times 10 to the front of that, which is exactly what it should do, because scientific notation is just a number times 10 to a power, and that would be a lot of zeros to write. My calculator automatically got rid of all those zeros, just turned it into scientific notation. So there's a couple of things I want to point out here in this problem about our shortcut. Let me go ahead and label this H plus concentration. Make sure we've got that there. When we're taking the log or the negative log of a value, a scientific notation value that has 1 as its base, then whatever that exponent is going to be your answer. So because we're taking the negative log, it is the negative of the exponent that we're going to see as our answer there. So we can already predict for this next problem that once I take the negative log of this number, which is going to be my first step to find, in this case, my pH, that it's going to be 8. That's all I need to know. I probably wouldn't even plug this into my calculator, but you can, and it will turn out to be 8. I'm going to make sure that's 8.0 here to keep my sig figs from my original value. But if it's base 1, then the exponent is the value of the negative log that you're taking there. Just make sure you turn it, positive. Switch the sign on that. And then that also kind of parallels with what we're seeing here at the end. If we have 10 raised to the negative of a whole number, an exact whole number, then the scientific notation is basically just going to add that 1.0 to the beginning of it, because whole numbers are allowed in our exponent. If this isn't a whole number, if that's even times 10 to the negative 8.9, that's not allowed in scientific notation. That's just not how it's done. That's just the rules. Which means when you plug that in to your calculator, if you did something like 10 to the negative 8.9, then it's going to change the base, isn't going to be 1 anymore, and that exponent will end up being 9, but the base will change in order to get that into proper scientific notation and be equal to this value. So when you have nice round pHs and pOHs, nice whole numbers there, and or if you have scientific notation concentrations, the base being 1, you can do all of these negative logs and these answers in your head. You still need to show a little bit of work if this is in the free response section. Multiple choice though, go for just the quickest, easiest way you can get that answer. We didn't used to always be able to use calculators in the multiple choice section on these tests, but I don't think they've changed the problems that significantly to add it back in. They've just tried to level the playing field so everyone has equal access and opportunity. But if you know how to take a negative log in your head, you know to just check that exponent. And there is actually a trick for how to estimate logs that aren't base 1 as well. I'll tell you about that later. Do what you got to do in order to find a nice quick answer to save time on that multiple choice section, especially if you see some simple logs ahead of you. So to finish out this part B here, if my pH is 8, then my pOH is going to be 14 minus 8. I'm trying to add an extra decimal there where I don't have it or need it. But that means my pOH is going to be 6.0. And now when I find my H OH concentration, like I did last time, I'm just going to go through the 10 to the negative root. I know the equation's not on the equation sheet, but it's easy to remember. A lot of calculators, the log button, like you push second and then the log button, and that's the exponential, the 10 to the power. So it's like to undo the log button, you push second log, and it just undoes it, kind of like sine and inverse sine. So in my calculator, I could plug in and type in 10 raised to the negative 6.0, but I already know it's going to tell me the answer is 1 times 10 to the negative 6. I'm going to make sure to keep those 2 decimal places there on my answer, or 2 sig figs, sorry, 1 decimal place. And that's our final answer here. So, similar process with each. We just got to keep in mind our H's and OH's that we've got. We've got a couple more examples that I'm going to go through, but you might decide to kind of pause it here and try these out. I know this next one looks a little bit weird because we don't have scientific notation. Technically, you could turn that into scientific notation. It's just 1.00 times 10 to the negative, or no, times 10 to the positive 1. And I'm just going to point out, since my exponent is positive, I know my pH here is going to turn out to be negative, which is actually also going to be the case in E as well. We're going to have a negative pH. So don't let that scare you. I told you before it was possible, and I'm telling you again, when you do this calculation, you're going to see it. These aren't even that crazy concentrations. So I was telling you with part C, you can turn that into scientific notation in order to be able to take the little tricks that I showed you and not have to plug this stuff into your calculator. But the first step is going to be the same even if you did do it in your calculator. You're just going to start by taking the negative log, because this is a concentration of H+. So we take the negative log of that, H concentration, we get our pH. So even if you don't know the trick and you're not really good at taking those shortcuts with math, that's fine. Take the long way around. Just don't let these numbers, when they're not scientific notation, throw you off. You can still take the negative log of a kind of whole number, a normal looking number there. So you've tried it. Now let's go through this process and see if you get the right answers. You could probably skip to the end to check them and then just scooch back a little bit to get help if you need it. But I'm going to go through this process with you. And I already told you my first step would be to take the negative log of that concentration, giving me my pH, which would end up being negative 1. I'd make that 1.0, of course, because keep in my sig figs. I might, in fact, say that that should be 1.00, because that does have 3 sig figs in its original form right there. And now I'm going to subtract from 14 to find my pOH. So 14 minus negative 1 is going to be like 14 plus 1, which means we're going off scale this direction as well. And remember, we keep the decimal places as our original measurement when we do the subtraction, which means I'm keeping 2 decimal places here, making our pOH 15.00. And then to find my OH concentration from there, I need to do 10 to the negative of my pOH. So I'm doing 10 to the negative 15. Go away. There. And that is 4 sig figs total, which means when I get my answer out here, I need to make it 1 with 4 sig figs times 10 to the negative 15. Couldn't fit my times 10 in there, so I just did my E, which works just as well, means the same thing. but making sure to get 4 sig figs in there. That times 10 to the negative 15th molarity, of course, is our concentration. I just realized that I had not classified those last two solutions in A and B as neutral, acidic, or basic. I knew I was going to forget it. I emphasized it to you. If we look back on those real quick, and I don't want to disappear all of this stuff, remember we need to look at the pH value in order to see whether it's an acid or a base. So part A, our pH was 9. That was bigger than 7, which means we are a base. In B, our pH, we calculated it earlier on, but we still look at it the same. pH is 8.0, also bigger than 7, which makes that also a base. In this one, our pH is negative 14. Negative 1, my bad. Still negative, which means that it is less than 7, which makes this an acid. And now let's finish out these calculations and not forget to classify each of these before we move on. So our D, I have an OH concentration, which means when I start taking my negative log here, I'm going to be finding my pOH. So 1E negative 3, which ends up being, surprise, surprise, 3, which then I can find my pH by subtracting from 14. 14 minus 3 is 11, keeping 1 decimal place on this. Then lets me calculate my H plus concentration as 10 to the negative 11, which is going to be 3 sig figs, 1.00, times 10 to the negative 11 as my molarity, as my H plus concentration. Now looking at my pH, this is bigger than 7, which means this is a base. This next one, I already made a comment, is going to have another negative pH, and we're going to see that right away because I have an H concentration. So when I take the negative log of this number, it's going to be giving me my pH, because I'm taking the negative log of the H stuff here. And this time is the first time we don't have a 1-based number, which means this is the first time, not only, well, I guess it's not the first time it's negative, but we kind of need to look at our unrounded number. Make that look a little bit more like a 2. So my calculator is telling me this answer is negative 0.30102. I want to keep 2 sig figs just like I was given. That leading 0 does not count. So my pH here is going to be negative, all important negative 0.30, which means that my pOH is going to be 14 minus negative 0.30, which means my pOH is 14.30. One more step, just like normal, to find my OH concentration. I'm going to be doing 10 to the negative of my OH concentration, of my pOH, which once again, because this is a decimal, it's not going to give me a nice round 1 times 10 to the something. And if I try and write it out as 1 times 10 to the negative 14.3, it's not a proper number. It's not correct. Just plug it into your calculator. It'll fix it right up. Mine tells me this answer is 5.01187. It keeps going. But that's E negative 15. Just kind of go sideways real quick. This isn't my final answer. And I do want to keep 4 sig figs because that's what I ended up with after doing my subtraction and keeping the correct number of decimal places there. which means 1, 2, 3, 4. The 8 is going to round that 1 up. So my final answer here is going to be 5.012 times 10 to the negative 15th molarity. So, yeah, it gets a little bit, more technical and roundy when you have numbers that aren't base 1, nice round pHs and pOHs, but you go through the same process. So, don't let the sig figs and the rounding scare you off here. I would put money on the one sig fig point, because remember, it's only 1 point in the free response, where they're looking at your actual work to see if you've rounded things correctly and not just looking at multiple choice question options where they've rounded them for you. I would put money down that they're not going to make the 1 point in the free response something that is related to pHs and logs and subtracting, because you have to switch back and forth between sig figs and decimal places. And remember that map is circular. You can go through multiple different directions, multiple different steps, and if you do your multiplication and your subtraction in different order, then they can come out to be slightly different answers, and yet they're both perfectly correct. They're just going to be very similar to each other, but the sig figs, the rounding, and thus the value could be different. And the graders' rubrics are already insane enough. I'll show you more of those when we get closer to the test, but they're not going to make them even crazier by giving multiple, exponentially more different paths to get to these answers and different roundings on each of those paths. So I would put money down that they're not going to make this the sig fig point. So do the best that you can on the rounding, and don't beat yourself up if my answers look a little different than yours. Make sure you look at what process I'm using, especially if you're going a different direction than I am, going through different equations. It doesn't make your answer wrong at all. It's probably perfectly correct, and I will definitely go through that process of checking every individual answer and variation that you can get to make sure, if you're close, that you went through the right process and rounded correctly, whatever direction you took. So, I've got one more quick question on this page that does not involve half as many calculations as we just did on the example 1, but another kind of real life situational question that we could, be standalone. Asking us to find the pH of a specific molarity concentration of potassium hydroxide. And so for this one, the first thing, I know I've got a molarity, I know I've got a concentration here to work with. My instincts are screaming at me to take the negative log of this number, but it didn't tell me whether this is an H or an OH concentration. We've got to be able to decode the solution, the name, turn it into a formula to see if this is an acid or a base, if it's going to be an OH or H-based solution moving forward. So this is one of those times, like I told you, nomenclature isn't going to be directly tested on the test. But there could be times when, through context clues, like that name, that nomenclature, you can figure out a little more information. They might have had something else somewhere else in the problem, but just knowing potassium hydroxide is going to be KOH, which is a strong base, which is going to break off and form an equal concentration of OH ions as the amount of KOH that is put in there originally. This concentration is essentially the hydroxide concentration. So when I take the negative log of that value, then I'm going to be finding my pOH, which isn't exactly what I wanted, but I am still going to be getting closer to what I was looking for. When I get that answer out of my calculator, it's going to tell me it's 2.8170, and I do want to keep 3 sig figs, just like my 3 sig fig given, so that 7 is going to round my 8 up, so 2.19 is my pOH. And then just one quick step to get to my pH. We got to subtract from 14. Keep 2 decimal places there. Is going to be 11.81. That's my pH. That's what it was asking for. Had to take multiple steps, even though it didn't ask me for my pOH. That was really the only way to get to the pH. Well, I guess there's always two ways to get there. I think it's a simpler way to get there. Like I said, my eyes see a concentration, my instincts scream, take the negative log of it, turn it into a pH or pOH, make it into normal numbers that are easy to work with. And so, at this point, I've done all of the calculations that I am going to do. You, on the other hand, should practice some of these calculations on page 9. If you haven't had the opportunity to yet, and you'll notice that several of these have some nice base 1s in those concentrations, or some nice round pHs. Here, I guess not so many, but that you probably don't even need a calculator for. You could do those using our little trick with the nice round numbers. If you need help with any of these, if you're not getting the answers or you're doubting your answers, please come in, get help, or check your answers with mine. I have my work shown, and we can talk about any variations you got, but you got to be able to do these calculations because these are going to be the foundation. These are only our strong acids and bases we've been working with, finding the pHs here. Next step is to do the same thing with weak. And even though there's some more stuff to it, it will come back to these same general calculations. So let's get good at them, get confident, and then we can move on, finish out this unit.